Putala, good morning. Hello. Lamai. Good morning.
Good morning, sir.
Okay, very good, Puta. Very good.
Morning, sir.
Very good. So today we will try to understand something with no doubts, Puta. That is very important. Yeah, something with no doubts. Let's say we are going to compare this steady flow energy equation related system. With against, or let's say, and closed system comparison. Okay, I believe we have learned something about steady flow energy equation. I think before last Friday, if I'm not mistaken. Even last Friday, maybe last Friday. Last Friday, yeah, I did the lecture from when I was in the university at that time, morning time. Yeah, if I'm not mistaken, yeah. Steady flow energy equation related system. So steady flow energy equation. Equation related system. Okay. Related system and closed system. Okay. Comparison. Okay. Here we are going for a comparison. Yeah. So I have done it all right, if I'm not mistaken. Steady flow energy equation. We have developed the slides together. So let's say comparison. So here in the comparison, yes. And closed system. Okay, comparison. So let's see how we can compare this. Yeah. Steady flow energy related system and closed system. So steady flow energy related system means a system compatible or in agreement with steady flow equation, steady flow energy equation. Okay. And closed system is about, based on the definition, we have to understand what closed system means. And here also we will look into the energy aspects. Yeah. See how this study goes. Yeah. See how this study goes. Yeah. You can focus on this. No need to write anything maybe, but any important thing you can take note. Yeah. So let me draw, as I mentioned to you, a generalized model. So we are comparing the models. Even that day, if I'm not mistaken, we have discussed some models, compressors, condensers, boilers. Uh, I think we have done the comparison, if I'm not mistaken. So let's say the steady flow. You have in and out. You have in and out. Okay. Same mass flow in and out. Okay. So let's say this is SFEE system. Okay. SFEE system. System agrees with SMEE, SFEE agreed system. Okay. And the other is closed system. Okay, these are thermodynamic systems. Huh? So closed system. Closed system. So here, for closed system, if you have in, yeah, we know that there is no in. Okay, there is no in. Interesting. Okay. Also out. There is no out. Okay. There is no out. No in and out. And also there can be work done on the system. Let's say W. Okay, let's say W. W. So work done. W. Good. W. Okay. And for closed system, there could be W. Okay. There could be W. And when it comes to heat, when it comes to heat, okay, when it comes to heat, because if no heat and work means that system has no much functionality, okay, because out of the system there should be heat in or out and also work in or out. Okay. Yeah. I can see 40 plus students. Very good, Putana. Yeah. Q. Oh, heat. positive head. Of course, when it comes to systems, yeah. So this mass in and out work network normally towards in we consider, and also net heat towards the system. So we consider the standard direction. Standard means the positive direction. Yeah. So the slide. I will go for the comparison. So steady flow agreed system. I just put steady flow agreed system and closed system. Okay, closed system. SFEE agreed system. Let's see. So these are simple models. Okay, simple models. These are simple models. So under steady flow, there are a lot of systems in real application, and even under closed system, there are a lot of applications. Okay. So one more thing you should notice that with the mass flow in, there should be energy in as well together with mass flow, because flow contains some energy. So there should be in. Same way, together with M out, there should be E out. Okay. Remind me if there are any more to add. Okay. Remind me if there are any more to add. Yes. So this is how the situation is. Okay. So if you think of steady flow examples, yeah, let's see. Before that, mass in and out. Okay. So I will put same mass flow in and out. Okay, same mass flow in and out. Okay. For the closed system, same but no mass. No mass flows in and out. Okay, no mass flow in and out. Yeah, so you can say W work. Okay, W is work. We would say crossing the boundaries, okay, of what? Boundaries of RIS, boundaries of there is a boundary of the system. Or we call that control volume, because system, it's a volume, it's a space really. System, or we use the other word, control volume. Okay, control volume means it's a control space. Space has a volume. Okay, that's why control. Interesting. Volume or space. Yeah. So for the closed system also, W crossing the boundaries of the system. Here, let's say even you can put as control volume, but here I take this out. Okay. So you may ask a question, why left side you put a control volume and why not right side? We don't have anything. So I would add the word closed system, okay, to fill that one. So of the system, of the open system here, open, or let's say, yeah, open system, open system. Yeah. So open system has a control volume. So that is in and out. Let's see what happens in the closed system afterward. Yeah. Also there is Q. Q. Heat crossing the boundaries. Okay. Q. Heat crossing the boundaries of the closed system. Okay, heat crossing the boundaries. Interesting, eh? Yeah, interesting. I will make the fonts a little bit big. Oh, no. Not bad. Okay, good enough. Huh? Yeah. So what else? Work, heat, mass, and other energies, flow energies here in the open system. Okay, agreed open system. Okay, SFEE agreed open system. Good. This is closed system. Okay. Yeah. So any more here? Any more here? Are you okay with this? Okay. Yeah. So this is what we call the physical model. Physical model. So left side, no matter it's a boiler, a turbine, okay? Yeah, we have discussed this very well. And the right side, also there can be similar applications with no flow in and out, okay? So let me continue this. Let me continue this. I'll do this way. Actually, I have started this earlier by discussing the applications. Yeah. Nice. Good. This is how this open system and closed system. So now I'm thinking of closed system example because we have discussed something about the open systems. Yeah, let's see. Be patient. Be patient. So I will take some closed system example. Okay, let's say I take can you remember the steam table lab data, the physical properties? Let's say we have something here. A system with a boundary and let's say this is a closed system. Okay, so let's say this is a closed space. Okay, this is a closed space. Let's say this is a cylinder. And a piston. Cylinder and a piston. Okay. Oh, let's say closed space. Later go for cylinder and piston. Let's say gas cylinder. Okay, gas cylinder. Okay, gas cylinder. Closed space. Gas cylinder. So gas cylinder means you have a boundary. Okay, you have a boundary. It is fixed. Okay, fixed boundary. What boundary? System boundary. Okay, let's say fixed. When the boundary is fixed, you can say this has a fixed volume. Okay, this has a fixed volume. Let's see. In this, so if just leave this, just leave, let's say example, your gas cylinder in your kitchen or in a restaurant or elsewhere. So if you leave this as it is there a heat transfer? No. Any work transfer? No. Okay, you of course you are not using the gas here for cooking. Yeah? So this is all closed. Okay, so here there can be molecules. Okay, there can be molecules. There can be molecules. Okay, this is the closed system, and there can be molecules. Okay, see, so there can be molecules like this. So if no heat and no work here, if no heat and no work, if no heat and no work, there is no functionality of this. Okay, there is no functionality of this. So this is what inside. This is what inside. So if no heat and no work, there is no functionality. Let's say to make it function, if we add heat, let's say if we add heat, if we add heat, you can imagine when we are adding heat, the system is energized and things will be getting changed. Okay, things will be getting changed. So that is very important understanding. And things will be getting changed. So what are the things will be getting changed? Energy levels, internal energy levels can be changed. Internal energy levels can be changed. That's why you always keep this gas cylinders. If you have, generally you keep under a shade, because to make sure that the matters or the gas inside the cylinder, okay, is not getting energized. You have to make sure that if getting energized means there should be increase in internal energy. Okay, there should be increase in internal energy as a result. Okay, as a result, what happens? The pressure level, we call the internal energy, is related to the kinetic energies. So higher the temperature, higher the molecular motions. Higher the molecular motions, the force on the cylinder is more force on the cylinder. We call it pressure. Okay, we call it pressure. So because of delta U, there can be delta P as well. Delta means increasing. Okay, delta means increasing. Okay, increasing could be anything. Yeah, temperatures, because of the temperatures. Okay, because of delta U, the temperature will rise. Okay, temperature will rise, but anyway, for us the important is delta U. See, because of Q, for this system, you can see, okay, because of Q for this system, you can see the rise in internal energy. And this internal energy rise is reflected as the temperature rise. Because of the temperature rise, that is one thing. Another, you can notice the rising of the pressure. Okay, the rising of the pressure. So the primarily, this is just because of the rising of internal energy, the temperature and pressure rise is reflected. Okay, yeah, quite interesting. Eh? Quite interesting. So it is like this. It is like this. Still very simple, very simple step by step. This is what you see here. But especially for this case, as we take fixed system boundary, okay, fixed system boundary. So because of fixed, what happened is, because of fixed, your W is 0. Not to say W0, but here you can see work done is denied. Yeah, W0 because of the fixed system. No chance is given for a work done. Yeah, here that is the situation. It is practical. You know, this cylinder is so solid, so strong. It can withstand a lot of tensions and all stresses, and the work done is denied. That's why 0 work done. Work done is denied or not allowed. Not allowed because of fixed boundary. So how to make a fixed boundary? You can use very thick, okay, the and strong enough to withstand any pressure buildups. That's it. Yeah. So practically that's how you do this. Yeah. So work done is denied. Yeah. Quite interesting. Okay. Quite interesting. So W0 means this. So W0 means this. So I will take, for this case, just put W this way. Okay, W is 0. So here you can see the system. So your W is 0 and only Q is there. Okay. So very nice. So W is 0. This is a closed system process. Okay, this is an example. Okay, this is an example of a closed system process. Yeah, quite interesting. So here what happens is, so your input of Q. Okay, now if you think of energy balance, that's why you need only the understanding, and W is 0. So what happens is you have Q value. So you have a Q value. So your Q plus W is the total input of energy in terms of heat and work. Work input also will lead to uh, the energy interactions. Okay, so Q plus W becomes delta U. See, delta U. But for this case, W is 0 because this fixed volume or fixed system boundary means fixed volume because of this. Okay, because of this. So what happens is here as W is 0, okay, so here this equation can be simplified, okay, can be simplified as Q is delta U. So delta U and Q. So you have to understand what this Q in little detail. Of course, it's a kind of heat transfer uh, during a period of time. Let's say delta T time period. Okay, delta T time period. That is very important. So the relevancy, yeah, during a time period delta T, delta T period of time. Yeah. This is not mentioned, but practically you have to realize this. If this has a time factor, there is a time duration, let's say 30 minutes starting from previous. So now during this 30 minutes time, total heat net input is Q. W, not to say net is 0, but W is not allowed for this case. So net increase of internal energy is delta U. Okay, yeah, that's how it is. So Q is a kind of total during this time period of delta T. That is okay. Okay. Even you can have delta Q, OQ, that is up to us. So Q total, that is also okay. Okay. If this is Q total, even Q total during delta T. So let's say Q is okay. Yeah. So I have to add one more term here. This is quite interesting. It's quite interesting. This delta U has a proportionality to temperature rise. Okay, has a proportionality to temperature rise. Proportion. Okay, it's proportional to temperature rise. Okay, proportional to temperature rise. Proportion, I'm looking for that sign. Proportion. Let's see. Proportion. is proportional to, okay, this is not alpha, this is not alpha, but very close to this. Even you can say sometimes the infinity sign we are using, so proportional to the temperature rise. Okay, this Q is equal to delta U, and that is proportional to temperature rise. Okay, so this is quite interesting. So in maths, okay, in maths, proportional sign can be replaced with the sign of equality when you multiply this constant by, sorry, when you multiply this delta t with a constant. So this constant, let's say c times delta t. Okay, c times delta t, c times delta t. Okay, and since this is a constant volume process, so we will say this is CV, okay, CV delta T. Is quite interesting. So we have learned something as well. So you know how this came for a constant volume, because fixed boundary, fixed volume, okay. So finally, because of the energy input, the internal energy rise, and correspondingly there is a temperature rise, and there is a pressure rise as well, pressure build up, and all because of the internal energy rise. That's why sometimes these gas cylinders, if you apply more heat, even the cylinder can be damaged, and that could be a big accident as well. Okay, so this is what we learn here as part of a closed system. We consider gas cylinder as an example. Okay, gas cylinder here. So no, only 100% gas here. Let's say, gas. Yeah. So 100% gas, no liquid. Assume, no liquid here. Gas. Okay, only gas here. Gas, 100% gas. Gas 100% for this case. Okay, gas 100% cylinder. Gas cylinder. Okay, 100% gas. So from here, take the only delta U and delta T. This is the expression. Delta U is CV delta T. I hope you can understand this. Okay, I hope you can understand this. And I will go for a similar, another example. Okay, another example. This time also 100% gas with variable system boundary. Variable system boundary means the system boundary can be changed. Okay, so you have a variable volume. Volume can be changed. variable volume, variable volume. So here what we will do is, this is still the same. So shall we maintain constant pressure? Okay, constant pressure, closed space this time. Closed space. Yeah. So gas 100%. So this is not just cylinder. Now this has a piston cylinder. Okay, piston cylinder. So piston is moving. When the piston moves, the volume moves, system boundaries changing. Okay, now I'm going to use the same slide. I'm going to modify this. So this is the one. So closed system, you can have a look. Yeah, fixed volume, fixed system boundary, work done is denied, heat is applied. As a result, there will be delta U, and as the result of delta U, there will be a temperaturized delta T and also pressurized delta T. So quite simple, the energy balance. So energy balance. So you consider W as 0. So your energy balance, W is 0. So Q plus W is delta U, internal energy rise. So Q is delta U because W is 0. So the same equation here, Q is delta U, means is equal to delta U. And everything is proportional to delta T. So even, yeah, so this is right. This is right. Should be all right. I think you can understand delta U. Q equals delta U proportional to delta T. So this CV we call the constant of proportionality here. And this proportional constant is for constant volume. Okay, constant volume. Constant of proportionality is CV, so Q is CV delta T. And delta U is CV delta T. So if you need further about this, okay, if you need to know further about this, we would say if you need to know about CV, what CV means, this CV is delta U by delta T. Delta T. And the unit is, here we would say unit, okay? So CV is delta U by delta T. If you take 1 kg mass here, okay, or even you can have the big CV here, let's see. I'll put CV here, big CV, okay. So this CV means specific, not to say specific, constant volume gas, okay, yeah, gas, constant volume, let's say heat capacity, constant volume heat capacity. So or heat capacity at constant volume. Heat capacity at constant volume, or constant volume heat capacity. Okay, so the unit is kilojoule per Kelvin. If you think of 1 kg, that is CV. Okay, that is CV. Later I will revisit this slide. Temporary I will put the CV unit. This way. CV unit. Small CV I will take. Small c means specific, kilojoule per kilogram per kilojoule per kilogram per Kelvin. So this is small c. Okay. So this is specific c. Specific CV. So let's see. To take some space. Take some space this way. So see, is this this is heat capacity at constant volume. So specific CV is small CV. The unit is kilojoule per kilogram per kilogram. Okay, so that's the point. So per unit mass. If this system has this 100% gas system, if this has 1 kg, then exactly CV is kilojoule per kilogram per Kelvin. Okay. Later I have to revisit this slide. So later I will revisit the slide. Okay. So back to this. Now variable system boundary. Let's see what happens now. W is not zero because variable system boundary. Yes. So variable volume. Here I'm going to do this way. Okay. Here I'm going to do this way. Little bit. And the W value. No flow in and out. So I will take this out at the moment. So what happens now is this is your system boundary, constant pressure. Okay. Constant pressure. So what happens is in a constant pressure system, so when you add heat, if it's a fixed system, your pressure will be building up, or pressure is increasing. We call pressure buildup. So here, constant pressure system, Okay, constant pressure system or constant pressure system of closed space. Okay, of closed space. Okay, of closed space. So gas 100%. So this should be piston cylinder time. Okay, so variable system boundary. Okay, means variable volume. Difficult to manage here. Difficult to manage. Let me try. Let me try. Okay. Right. Let me try. Delta T period of time. Can you remember here? Delta T period of time. So when Q is there and when the pressure is constant, what happens is, so this is at T equals 0, let's say now, because of this work increase, what happens is the next you can see the variable portion of the boundary. Let's say this is the variable portion. So this is the variable portion. Right? Variable portion of the boundary is the variable. Variable portion of the boundary. Excuse me, Papa.
මොකක්දනේ මේක charge වෙලා නැහනේ. මොකුලක් දාන්න නැහැ.
Sorry, Bhuta. So you have to understand that the moving boundary doesn't mean this has some holes. Eh? Yeah, this dash line is to show the moving boundary. I think the best is how to say. I will use a different color maybe instead of this. Sometimes for the dash line you may be misleading. Yeah. But that is, I think that is okay. A dash line also okay. Yeah. So this moves, this boundary moves. Okay, this boundary moves. So what I will do is, as this boundary moves, since I mentioned about the piston cylinder, so let me draw the piston as well. So let me draw the piston as well here. This is the piston. Okay, this is the piston. So here you exclude the piston for the boundary. Okay, so here internally you can see the how to say the boundary here. This the moving boundaries in red in color. Dash the other boundary. Yeah, it's like this. So I'm thinking how to draw here. We will do this way. Let's see. During the time delta t, this piston moves. That's how it is. This piston moves. And this cylinder space, okay, becomes more. Okay, becomes more. So let me do this with that piston space movement. Yeah, now should be okay. This moves and sideways also there is a movement. Sideways. See how the movement is. Let me take this out. Okay. So That's how this volume expands. Okay. Now what happens is volume expands means it's a work done. See, it's a work done. Now I'm very sure you have a problem here. Why work done towards the system? Actually, this work done is out because the gas expands. But for the sign convention wise, we take W towards. So if this is 10 kilojoule work done, so towards the system, this is minus 10 kilojoule work done. Okay, during delta T time. Good. So Q is here during delta T time, W is here. Okay, W value. W work is here. Quite interesting. So this the right side, the molecules are here. So W is not to say 0. Okay. W is not to say 0. So originally W from here you have extra increase of volume. Okay, extra increase of volume. That's how it is. So you have extra increase of volume means there is a W. Okay, there is a W. Same corresponding. Okay, so the volume increase is there. The same space, the volume expands. That's how it is. That's how it is. I think the best is to have this expansion. And I will do this way. Yes. So you can see the volume expansions here. Okay, volume expansion. This looks very nice. I need to make it a little bit wider. It is like this. So the original boundary moves, okay, moves up, means the volume change. So variable volume. So that is obvious. Variable volume. So you can see constant pressure, system of closed space, gas 100%, piston cylinder, variable system boundary. So we can see the sideways increasing because of the piston movement. Okay, variable volume. Let's say here constant pressure means this is possible only by applying a resistive force here. Okay, so you can see only by applying a resistive force. So this is the constant pressure. So against this force, the piston is moving. So constant pressure. effort is here. Okay, this is the constant pressure effort. Constant pressure effect. So there can be a weight or something. Yeah. So when delta P going to, when the P going to increase, instead of P increasing, this creates a space. Okay, this creates a space. So that's how this has extra space. Now, if you have any questions, just let me know. And now you cannot say, I take the flow out, flow out here. This one. No need to put the, no flow in and out. I just take it out. Yeah. So now you cannot say work done is denied. Work done is a must. Yeah. When Q is there, for this situation, work done facilitates constant pressure process. Okay. Work done facilitates means support. Okay. So work done means what? The gas expansion. When there is a gas expansion, means the increasing of volume, means pushing the boundaries, means pushing the boundaries means work is being done. So the work done. So when Q is there, work done or gas expansion is to maintain the constant pressure. That's what we call the facilitates. Okay, supports, helps to maintain, okay, constant pressure within the system. Now we got a practical, so you have to understand the practical aspect of this. Okay, you have to understand the practical aspect of this. So then what happens is your energy balance. Energy balance means the conservation of energy principle. We call it first law of thermodynamics. Don't worry. You will learn first and later you will realize it. So you have Q plus W. Okay. Is delta U again. Q plus W is delta U. Okay. Now let's see what happens. Okay. Now let's see what happens. I bring this here. Now there can be delta U. Okay. There can be delta T, but delta P is 0. Essentially 0 because constant pressure. Understand? Because of the constant pressure process. Okay? Delta P is 0. Constant pressure process. Quite interesting. Eh? Internal energy can be increasing, temperature is increasing. P has no change. But you have what? you can have delta V. Okay, you can have delta V. You can have delta V. Means increasing of volume, because W is there because of delta V. No delta V, no W. Delta V there means you have W. Okay, so now let's see. Now Q plus W is delta U. So now I will take, this is delta T. Okay, so I'm writing the expressions now. Yeah, let's say this is a closed system. Try to understand. Yes. Now, I will write this way. Delta U, I will write as, let's say, delta T. Before delta T, it is 1. And after delta T of time, okay, and delta T. So during delta T, let's say, this way. Delta T time, delta U is, let's say, U2 minus U1 delta U, okay, at time delta T. And delta T you can write. So U means 2 means after delta T, you can consider it as 2. Okay, and before starting delta T means just at the start of delta T, you consider that is the situation 1, or we call state 1. Okay? So you have 2 states. So state 1, 1. When what? Delta T starts. Okay, let's say that is state 1. Quite interesting. State 1 when delta T starts. And you can have state 2. Okay, when delta T ends. Okay, at the end of delta T, state means a condition. Okay, it's like a condition. Okay, so you imagine state 2 means everything here for the new V2. So everything for state 1 is at the initially, at the beginning. Okay, at the beginning, of delta T, that is state 1. Okay, so state 1 you have, so for delta T is from 1 to 2, delta U is U2 minus U1, and delta T you can see if you need as T2 minus T1, and delta V you can write as V2 minus V1. Okay, V2 minus V1. So delta P equals 0 means you can see P2 is P1. Okay, P2 is P1. P2 is P1. That interesting. Hmm. I don't know how you can read this on your display. It can be a mobile, it can be a computer, but hopefully you can see this well. System for this case. So constant pressure system. This is a constant pressure system. Constant pressure system. Yes. Good. Okay. W is yes. Since I have no space on this. Okay, good. So Q plus W is delta U. Okay. And so W is quite okay. Work done because you have a pressure, same pressure times the volume. Okay, volume increase V2 minus V1. V2 minus V1. So when you put V2 minus V1. This is an expansion, so W direction is towards, so we put minus sign. Okay, because by right this P times the volume increase is the work done from the system, but towards the system I use minus P2 minus P. So Q plus W is delta U. So W, I will put minus PV2 minus V1 is delta U. Okay. Yes. So delta U is, what is delta U? Is U2 minus U2 minus U. Okay. Yeah. So for this case, you can, if you write Q is equal to, if you rearrange the things, U2 plus PV2. Okay. Let's see. U2 minus U1. So this becomes plus P V2 minus V. Okay, P V2 minus V. Let me get some space here. Is equal to U2 plus PV2. V2 minus, okay, U1 plus PV1. Can check. This is okay. This this is equal to u2 plus pv2 means, okay, h is u plus pv, okay, h2 minus u1 plus pv1 means h1, okay, h1. So that's how you can see the evolution of the formula H2 minus H2 minus H1. Also, you can see there is an increase in delta T, so proportional to delta T. Okay, H2 minus H1. Or you can say this is delta H, delta H. Delta H. Yes, you can see that. For a constant pressure process, or in a closed system, and if the pressure is maintained, heat increase becomes the enthalpy change. That's why we have learned this
Sir,
H.
may excuse me, sir.
Oh, sir.
Sir, may අර මේ W සමාන ඍණ P ආවේ කොහොමද? ඍණ P V2
W.
ඍණ V1.
ආවේ මෙහෙමයි පුතා. මේකේ වොලියුම් එක වැඩි වෙනවා කියලානේ ගත්තේ. V1 ඉඳලා V2 වලට. මේ පේනවනේ රූපෙත් නේ. එතකොට වොලියුම් එක වැඩි වෙනවා කියන්නේ W කියන එක සිස්ටම් එකකින් තමයි perform කරන්නේ. ඒ කියන්නේ මේ තියෙන ගෑස් එකෙන් work done එකක් එළියට දීලා තියෙනවා. තේරුණාද පුතා? එතකොට W කියන එක ගත්තාම ඒක PV2 minus V1 කිව්වොත් හරිද? මෙන්න මෙතන. මේ PV2 minus V1 කියන්නේ system එකකින් දෙන එක. Outwards, system to surrounding. තේරුණාද? W
ඒ
කියන්නේ
කියන්නේ මේ ඍණ කාර්යයක් කරලා කියලා කියන්නේ කාර්යයක්.
අන්න හරි. නෑ නෑ. පද්ධතිය තුලට ඍණ කාර්යයක් කරලා. Towards the system. ඒ කියන්නේ පද්ධතියෙන් තමයි කාර්යයක් කරලා තියෙන්නේ. ඒ කියන්නේ පද්ධතියට කාර්යයක් කරගත්තා නම් ඒක මයිනස් වෙනවා. දැන් මේ sign convention එක W වල direction එක තියෙන්නේ පද්ධතිය තුලට. වෙනවනේ මේක පද්ධතිය තුලට තමයි තියෙන්නේ ඒක. ඒ වුණාට ඇත්තටම කාර්යයක් වෙලා තියෙන්නේ පද්ධතියෙන්. හරි නේද? ඒ කියන්නේ මේක තමයි මම මෙතන වෙනින් මම equation එක ලියන්නේ. Let's see. ඇත්තටම නම් වෙලා තියෙන්නේ minus W කියන්නේ PVT minus P times V2 minus V1 නැත්නම් W කියන්නේ minus PV2 minus V1. තේරුණාද? minus W කියලා කියන්නේ minus W කියන්නේ from the system to surrounding is minus W. Minus W කියලා. With the system to surrounding now plus W කියලා තියෙන sign convention. නේද? With the system to surrounding now sign convention එකට අනුව second. System to surrounding. System එකෙන් surrounding එකට තමයි W කියලා තියෙන්නේ. ඇත්තටම W එකක් තියෙන්නේ surrounding to system. ඒ කියන්නේ minus W එකක් තමයි මේකෙන් වෙලා තියෙන්නේ. Minus W කියන්නේ P times V2 minus V1. හරි නේද? V2 කියන එක increase එකක්. ඒක හැම වෙලේම ගන්න delta කියන එක increase එකක්. ඒකට delta V කියන්නේ වැඩිවීමක්. එතකොට මේකෙදි pressure times delta V කියන්නේ work done එක. ඒකට වැඩි වෙන පැත්තට නම් work done එක තියෙන්නේ from the system. To the system නම් ඒක minus W එකක් තමයි. Minus W is PV2 minus V1. Then plus W means W. W කියන එක ඉන්නේ minus P V2 minus V1 minus W. Put it on with minus minus W. You know, W is minus. Okay. Q plus W. W can minus P can minus. W can minus P. So Q plus W can minus P V2 minus. So when make a theory now, P times volume change එක තමයි work done කියන්නේ. දැන් ටික දැනගන්න මේක ඔප්පු කරන්න පුළුවන්. Pressure times volume change එක තමයි work done කියන්නේ. තේරුණාද? Volume increase එකක් නම් මෙතන V2 minus V1 කියපුවම we consider it as a volume increase. So when it's a volume increase, so this P times volume increase means pressure time volume increase is something like a work done by the system or from the system to the surrounding. But the sign convention says, the arrow says, this work done W is from surrounding to the system. If so, again work done because surrounding to system. So system to surrounding is minus W. That is pressure times the volume increase during the time period of delta T. Textbook so you can read the notes and try to understand. Okay? But anyway, understand should not be later. It should be right now. මේ වෙලාවේ තමයි තේරුම් ගන්න තියෙන්නේ මට. පොත කියවලා තේරුම් ගන්න කියලා මම මේ වෙලාවේ කියනවා නම් මේක එච්චර සාධාරණ නෑ උගටට පුතයි කියන්නේ. ලෙක්චර් එක යන වෙලාවෙම මේක තේරුම් ගන්න. ඒක පස්සේ මොකක්ද දාගෙන තව ටිකක් වැඩිපුර දැනගන්න එක it's a different issue, but this is the time for you to understand. Right now. So you can ask any question. Okay? Yeah. So, let's say now we have to move further. So I will move in this way. It's a new slide. New slide, but the previous slide I will take a snapshot to make sure previous photographic memory is there. That's why you see what is there. Hmm? So I will do this way, and then I will take the set of equations back. භාවිත ඇවිල්ලා තියෙන්නේ නේද? Take the snapshot out. භාවිත කියන්නේ we will take the snapshot. Good. Okay. So these are the equations. I will take from here this. I'll take this. I will end here. So this increase of delta T, and also you can see the system increase delta T and the system increase of H, that is delta H. So delta H is there, delta T is there. So same like here, you can see delta U is proportional to where is that? Delta T. You can see here with constant volume. Q is delta U proportional to delta T. So here for this case of constant pressure, you can see, of course, delta H, but anyway, T is also increasing. So delta H is proportional to delta T. So same like the previous one. So then we can see, yes, that's true. So this delta U proportional to delta T. So here is big C, small v. Same like here, yes, that's true, but it is something like Cp times delta T, delta H. It is something like Cp times delta T, because constant pressure Cp, so delta H, so the constant of proportionality is Cp, okay, Cp delta T. So if you think of Cp, okay, if you think of Cp, you can see Cp is delta H by delta T. Cp is delta H by delta T. And if you think of the units, this is kilojoule per Kelvin. So you can think of small Cp now. Small Cp. So big Cp is kilojoule per Kelvin, and you can take small Cp kilojoule per, if you think of 1 kilogram per Kelvin. So that's how it is. So you have, we need to summarize this. So now you can see small Cp. So if you think of this way, here Q is M times, sorry, Q is H2 minus H1. That's true. There will be difference, but let's say if the system mass is M, you can write again the enthalpy difference. So then here it is for 1 kg, because specific enthalpy H2 minus H1. Okay, now this is M delta H is equal to times delta H. But now it is, I believe it's familiar with you. So this familiarity is very important. So this is for constant pressure. Constant pressure. Closed system. Okay, constant pressure, of course. Closed system. So you can feel that here. Of course, constant pressure closed system. If no heat addition, there is no any function, so you have to add something. Q is H2 minus H1. M H2 minus H1 M delta H. Actually, even Q you can write MQ. So Q, small q is per kg heat addition. If you think of for 1 kilogram equivalent heat addition, but anyway, I take this out. Should be okay. So H2 minus H1 M delta H. That is equal to M what? Delta H is Cp delta T. Okay, Cp delta T. You can see the equation here. I will take delta H is Cp delta T. So here in times delta H means Cp delta T. Of course, here 1 kg means this is small Cp delta T. Okay, because delta H is Cp delta T. Is the reason, because delta H is Cp delta T. Very nice. Today, in this closed systems, understanding, learning of these two processes is very important. Okay, learning of these two processes, very important. Okay, so I have to add new slide. add a new slide. I have to add a new slide. As I mentioned to you, I'm going back to this constant volume process. Okay, I'm going back to this constant volume process. This one. Quite interesting. You can see a set of equations. I will put it here. Highlight this. Okay, to highlight this. Quite interesting. So here, everything is, all the equations are included, but if I take this equation again, I take this equation again, Q is delta U equals CV delta T. So here again, if you think of mass M here in the system, earlier also there is a constant mass system. Constant mass system means it's a closed system, whatever inside mass remains the same. So here in this case, I will take this delta U here as mass times what? Delta small d means this big U is for entire. So here big U means we are doing some drilling, understand? Big U means kilojoule. That's all. Kilojoule. Okay. And small u means specific. Yeah, and when it turns specific, internal. So big U and small u. So that's why. So here, M delta U means, of course, you should know what M means. M means the mass of the system. System in kilograms. In kilograms. mg. Mass of the system in kilograms. Okay. So m del U means kilojoule per kilogram. So m delta U again will be kilojoules. This is a kind of drilling. Eh? Yes. So same way from the previous, delta U is CV delta T. Delta U is CV delta T. So delta U is CV delta T. From the previous knowledge, the dividing by system mass, CV delta T by M. Okay, so delta U by M becomes small delta U, specific internal energy. And this one we will rearrange this way. CV by M. We join these two terms together times delta T times delta T. So now it is quite obvious. So if we rewrite this, CV by M means CV by M means per kg CV value. Okay, so CV by M means it is specific CV value, that is small CV. So delta U is small CV times delta T. Okay, so it's quite simple. So if you need again the big delta U, quite simple, means you have to consider the total system mass mCV delta T. Okay, so this is how we model the constant volume system. Constant volume means no work done, no chance for work done. Okay, no chance for work done. Constant volume. Okay, so in the other way, constant pressure. So how to explain that one day? Constant volume, no chance for work done. And constant pressure is something like, how to say, it's a special process again. So here, when there is energy increase, it is necessary for a work done to maintain the same pressure in the system. Otherwise, if the constant volume, pressure buildups, that's why. So if constant pressure, volume builds up or volume increase. Pressure buildup is a technical term. Increase in pressure, we call pressure buildup. So here volume increase for constant pressure process. So let me summarize this. So I will find this way. CP, CP, CV, Here we first learn about big CV. So let's put big CV in front. Then we have learned about small CV. So let's put small CV in front. Yeah, in front of big CV. Okay. Closed system. I will take from here. So all are for the closed system. This is obvious. Yes. Good. So this is the topic. Okay. Now I will draw out from here what? M. Okay. I will draw out from the system M. Okay. M. What is M? Important to know what M is. System mass. Okay. System mass. So what mass? Working fluid in general. Okay. So the system performs W means work done by the system means what's a system? It's a fluid, the gas. Let's say here is gas. Yeah. So this can be any fluid, gas, liquid or liquid gas mixture. Still, this is in generally okay. Don't worry. And there's this. So now I will start writing equations. Cp, sorry, Cv is m times Cp. Sorry, m times small cv. With any question, please raise. if you have any questions. Okay, big CV and small CV connection. So you know what big CV means? It's for the system. Okay. So you can draw here. Everything is also for the system. Okay, it is within. Okay, it's within. Yeah, it's within. Interesting, eh? Yeah, quite interesting. So now we will see the connections. CV equals MCV. Same for P. CP equals MCV. Why P suffix is here? Why P is here? Why P is here? Suffix P is there because this is constant pressure. Okay, constant pressure. Constant pressure. Okay, and same way for CV, you have V here, Y constant value. Constant value means unchanged volume. Okay, constant volume means unchanged volume. Okay, so then it has a physical sense. Okay, constant pressure means unchanged pressure. This is quite interesting because pressure is something like a force exerted on the boundaries, let's say, because of the kinetic energies or because of the momentums, change of momentums of these moving molecules. Yeah, exerting a force on the system boundaries. So this force, when remains the same, is assured by putting a piston here in this case, and of course there is a constant pressure force here, constant pressure effort, let's say constant force. Right? So against this force, the moving of the piston means maintaining a constant pressure in a practical way. Okay? In a practical way. So constant pressure also has bit practical sense. Okay, bit practical sense. Constant pressure. Constant volume also has its own practical senses. So later we will see. Okay, constant pressure. Yeah. But at what pressure remains the same, that is important. It is 1 bar maintaining 1 bar, 10 bar maintaining 10 bar. Yeah. So different CP values can be. Okay. So these two are some expressions. And if you further look into this, I will duplicate the slide and I'm going to add here another expression. Okay, that is delta U. Okay, delta U term I draw from here. For constant volumes, delta U plus M delta U. Okay, delta U is equal to what? CV delta T. Is equal to what? CV delta T is equal to M times small CV delta T. Okay, I hope you can understand this. Interesting. Okay. Same way, for this case, CP, I will add more. Unchanged pressures. Okay. Unchanged pressures. The other expression, same like U in constant volume. Here you have delta H, enthalpy change, M delta H, Cp delta T, that is MCP delta T. Okay, MCP delta T. And what is this? This is Q. Interestingly. Okay, this is Q. Equals MCP delta T. Quite interesting. Okay. Same way here. What is this? Q is delta U. That becomes the energy balance somehow. Q term appears. In this way. So what I will do is add this Q as a last okay. Here also I will add Q as the last. So two processes, constant volume and constant pressure processes of closed systems. Yes. Q equals delta U means that is the energy expressions. Okay, that is energy balance results this. Q equals delta H means that is again the energy balance. So series of knowledge here. Equation 1, I would say this. This is the expression 2. This is the expression 3. Semi-constant pressure. 1, 2, and 3. So, yeah, item 3 is energy balance. Okay, item 3 is Q equals delta U, U means energy balance. Okay, energy and work balance, you can have energy balance. That is okay because work also consider it's really stored as energy in the system. So anyway, interact with the other energies. Okay, quite interesting. Good. Nice. Good. So these are the two special cases about this closed system modeling, right? Thermodynamic modeling. So energy balance, we call this first law of thermodynamics. So energy balance. Later we will learn these words. Don't worry. So constant volume means unchanged volume. Unchanged volume. Unchanged pressures. Okay. So system in general is this. W and Q is there. M is there. Okay. So if you need to add more parameters here, for this case, I may add to make this completion, I may add delta T. I hope you agree with this because delta T has better relevancy, starting and ending of a time period. There only you see this delta other terms as well. Okay, so you have delta u's, delta v's, delta t's, and all here. All corresponding to small words. Delta U, delta T, delta P, okay? That should be there. Small p, delta V, and you have delta H, and delta small u, and delta H. And you have the M here, okay? Here, even now will add this. Where shall I put this? Interesting. Very good. Okay. Okay, Butala. Good. Mm, very good. Nice slide. Okay. Nice slide. Okay, Buddha. Good. Uh, very nice. So this is about the closed systems. Today discussion. Give me a second because I have to plug the charger. Give me a second. I have to plug the charger for the computer. Okay, Butala. So that's it. ප්‍රශ්න තියෙනවද පුතාලට? ප්‍රශ්න තියෙනවද ළමයි? Any questions? Are you all right? Any questions? Hmm? Any questions? So,
Excuse me, sir.
yeah, Puta. Tell me.
Sir, excuse me.
Oh, tell me. කියන්න පුතා.
Sir,
ඔව්. කියන්න. Yes. Hello.
sir, capital C and simple C mean තාපධාරිතාවයි විශිෂ්ට තාපධාරිතාවයි.
ඔව් ඒක තමයි. Very good. ඒක තමයි. P for C, capital C and simple C. Heat capacity and specific heat capacity. තාපධාරිතාවය විශිෂ්ට තාපධාරිතාවය. But one under condition of constant volume, we call it C subscript V. පේනවනේ? V තියෙන්නේ එකයි. නියත පරිමාවකදී කියන්නේ ස්පේස් එක constant. ඒ working fluid එක occupy වෙලා තියෙන සීමාව ගත්තාම ඒක වෙනස් වෙනවා. තේරුණා නේද? එතකොට constant pressure ගිහම ඒකදී working fluid කියන්නේ system එකේ working fluid එකේ I will add the keyword working fluid as well. See here the working fluid is here. So the space එක මේකේ අවකාශය working fluid එක තියෙන අවකාශය වෙනස් වීමක් තියෙනවා. ඒ කියන්නේ එතකොට අවකාශයේ සීමාව වෙනස් වෙනවා. Boundary change for constant pressure. So CP. So M times CP is big CP. So small c is specific. අනේ විශිෂ්ට කියවහම ඉන්නේ 1 කිලෝග්‍රෑම් එකකට. So විශිෂ්ට තාපධාරිතාවය small c කියන්නේ විශිෂ්ට c කියන්නේ තාපධාරිතාවය at constant pressure. නැත්නම් under constant pressure. That is big C. So big C is for the system, but small c is for the 1 kg of working fluid. තේරුණානේ? System එක තමයි represent කරන්නේ, but it is for 1 kg. It's a fluid or the working fluid property. We call it a property. Property. Any more questions? Give me one pattern in a delta T. Can you see the significance given to delta T? මේ delta T එකෙන් හිතනකොට පුතා ටිකක් අර තමන්ට practical කියන එක තේරෙනවා මේක. This is really practical. Any more questions? අනික තමයි having the things at your fingertips. අර fingertips වල තියෙනවා කියන්නේ ඇඟිලි තුඩු වල තියෙනවා කියන fingertips වල. කියන්නේ ඉන්නේ අපි තියෙනවා කියන්නේ fingertips ඕන වෙලාවක දෙන්න පුළුවන්. ඕන වෙලාවක ගන්න පුළුවන්. Fingertips. So this piece of knowledge must be at your fingertips. In your fingertips. Let's say fingertips knowledge. So fingertips meaning. Okay. Oh, Buddha.
Sir, when we consider the gas cylinder,
Yes.
It has output and input.
Gas cylinder, Buddha. So which gas cylinder?
Day by day use.
Day by day use එක පුතා එතකොට day by day use එකේ වෙන්නේ මේකයි. It is something like how to say I'm writing a word here, batch. Okay, batch wise or unit wise. You can then gas cylinder ගත්තාම input එකක් කියන්නේ we fill it first and we are consuming. So one time fill and then using it for 1-2 months for long time. Delta T is there, everything is there, but mass is coming out. තේරුණානේ ඒක පාවිච්චි කරනකොට පුතා එතකොට ඒක මේ so you ඒක පාවිච්චි කරනකොට that is ඒක open system එකක් කියලා වෙනම කියන්නත් බෑ closed system කියලා කියන්නත් බෑ. We have to depends on the situation we can analyze. Depends on the situations. Yeah. So actually when the gas is released, the pressure change there. ඒක pressure එක වෙනස් වෙන්නේ liquid එක ඉවර වෙච්චා. Okay, it's a two-phase one. And let's see when I draw it, it is something like this. Let's see. I will draw the gas cylinder. Let's see. This is the gas cylinder. The gas cylinder under. Let's say this is the gas cylinder. Here you can see liquid, portion of liquid. Okay, portion of liquid and let's say so you have some liquid here and gas. Okay, liquid and gas. Okay, let's say this is your liquid. Liquid. Put it here. Okay, put it here. And your gas phase. This is your gas phase. Gas phase. the internet taking gas cylinder එකක් වාගන්න පුළුවන් කියලා හිතුවා. Let's say. Okay, this is the one. Let's say when you buy this, okay. This is the liquid gas. Liquid. My part of that. Gas. Either. Okay. So, Mickey. Gas. Gas. Liquid. Okay. High pressure. So, ambient temperature. The pressure is high pressure somehow. So when you consume this, when you consume gas, okay, let me draw the pipe. This pipe, let's say this pipe starts here. Let's say this is the pipe. Let me call it in white. Let's say this is the pipe coming from here. Okay, the gas come from here. Okay, here we fix the regulator. Okay, regulators. So the gas vent is this. Here is the gas vent. Vent means the gas lever. Okay, gas lever. So gas color, let's say green. Okay, this is the gas leaving through the regulator. Okay, the regulator is there. Okay, to reduce the pressure, because here is a very high pressure. When you regulate, okay, regulate means you have a hose connection. Okay, you have a hose connection. So let me draw the hose connection. Regulator let's see. Let me draw the regulator. Again, I just draw regulator. What regulator? Pressure regulator. Okay, pressure regulator. Pressure regulator, let's say. This one goes to here. Pressure regulator. Here. So this is the gas pipe. So this gas pipe generally, let's see if you want to take the, generally this should be taken as when we use refrigerant filling, so will we fill all in liquid form. And when we take the refrigerant out, so I'm to take this one. The pipe මෙන්න මේ liquid form එකටම තියනවාද? Okay. Or will it stay at the gas phase somewhere here? මේකට මම ඉතර හිතලා නැහැ පුතා. කවුරු හරි දන්න කෙනෙක් ඉන්නවද? I believe this should come down. This should come down. If this comes down, it's hard to say this one. I believe this should come down. Yeah. For the performance, for the effective delivery of gas, this should come down. But for the safety, I don't know. Okay, for the safety, because if you take the gas here, okay, anyway, and then we take the gas out. Okay, so here, same pressure, every other same pressure. This is pH, high pressure. So even you can see this sometimes in liquid form until this reaches the cooker. We can see here some liquid bubbles. If you have a transparent hose, you can see liquid here a little bit, possible. Okay. Why this comes down? Why not it's here? Oh, is it here or is it there? You have to think this. Right? Yeah. So you have high pressure. High pressure. I have no idea. Low pressure. Okay. High pressure, low pressure. So regulator is there, and this is the receiving. Okay. And supply gatham, there is one more maybe here to supply. Supply, once you supply here, okay, let's say this is the level of liquid. Okay, that is the level. Anyway, that's why we measure this in mass. So this is 12.5 kg. So when you consume, the more comes out here, the more comes out. Let's see, this way. When the more comes out, okay, you can see this level drops. This level drops. This level drops. Pin hollala balanne gas tiyanawada kiyala. And this is dropping and dropping, yeah, to here. Let's see, now we have only 37 students, including myself. So this is dropping, but the pressure remains. As long as two phase phase is there, the pressure remains oh, constant ambient. Pressure remains same and high. Pressure remains same and high, and we maintain constant ambient temperature. Constant low ambient. That's why I had to put this under shade. Okay. If the ambient increasing, your pressure goes some more high here. So that's a risk. And even the leaving pressure can be high. No, not because this may be flow metering. That's why. This may be a flow metering, let's say. So pressure remains high until the last drop of liquid vanishes. You have the same pressure. So after that, you are receiving only the gas. Means when you shake the gas cylinder, you feel that no sound of liquid, means immediately this starts, pressure drops. Yeah. So that's the point. Yeah. So high pressure here, high pressure. High pressure. Now we are high pressure liquid gas ore. But once the liquid disappears, once the liquid disappears, pressure starts to drop down. Pressure එක අඩු වෙන්න ගන්නවා. So that's the beauty of high pressure liquid. Maintaining here, you have a heavy weight, certain reasonable weight, say 12 kilograms, you can use for 1 to 1.7. But until the last liquid drop, the pressure remains. The pressure remains. The pressure remains high. Remains the same high. The same high level. Remains at the same high level. So it is something like this. So you can take the gas out. Yeah, somehow in liquid form, anyway, you are receiving the gas to the stove or to the cooker. So till the last liquid drops, the pressure remains, and this is something like a storage only. So this acts something like a storage. Okay, acts something like a storage. Anyway, there are auto filling, but here you have no auto filling. You have no auto filling, but when all the liquid finishes, means consider this is finished. The reason is, okay, yeah. So this is something like a storage, and considered, so acts like a storage and disappear in liquid. Okay. Disappearing liquid considers the cylinder is empty. Why? Make a liquid disappear වෙච්ච ගමන් මේ cylinder හිස් කියනවා. gas පොඩ්ඩක් තිබ්බට it is empty. Why? What's the reason? Okay. What's the reason? Now, let's say only liquid, okay, and only gas. You imagine only liquid and only gas. Only liquid mass is almost 1,000 times only gas. Of only gas. So here 12.5 kg comes as liquid because the gas volume is nothing here. Okay, the gas here, but the liquid is the mass. The only liquid mass is 1,000 times. Let's say almost. Yeah, almost 1,000 times only gas. 1,000 times of only gas. Only liquid. Okay. In a cylinder. Okay. So this is the situation. So in a cylinder, only liquid is 1,000 times. So once the liquid is gone, you may have little amount of gas, but you consider it's empty because compared to liquid, so here 12.5 kg, it's considered gas. Sorry, consider liquid form, pressurized, okay, high pressure. Yeah, little, of course, little mass is there corresponding to the amount of gas. But always the mass here, the most significant is the liquid. So this is the gas cylinder. So you consider this as a storage. Other than the storage, there is nothing to do with this. Okay? Other than storage, there is nothing to do with this. And by right, this pipe should go until the liquid level, until the bottom, because if this is remaining on top, only half to receive the gas only, you cannot have big flames. Let's say to have big LPG burners, you cannot use. If you take only the gas from the cylinder, you are really receiving liquid, but when it comes out, it is only gas. Because there are LPG burners as well, not only the gas cookers in your home. So I don't know whether you received the answer. I have no idea, but I believe you got some inputs. Yeah. So I have a question, not about this one. This one. Understanding gas leaks. Okay. Practically the බලන්න පුතා. So what gas leaks means to you? Let's say understanding gas leaks. Let's say here, I will take the same picture. temperature. Let's say you have liquid here. This is your liquid level. Let's say instead of this, yeah, okay. Let's say there is a little crack. Generally, when there is a crack, it is disastrous, but let's say there is a crack. There's a crack here. Okay, there is a hole. You know that there is a stream of gas coming this way. Even coming this way. Even coming this way. You can see the gas flow because you feel it. If you hold this, you may feel it. Okay? So this is how the gas leaks. Okay. So gas leaks. See how many students are there? 35. 2 more left. Yeah. So what this means to the gas inside cylinder? What this means to the gas? Okay. What does this mean to the gas? Okay. Gas වලට මේක කොහොමද තේරෙන්නේ පුතා? Let's see. For the gas. How the gas fail this? What this leak is for the gas? So, what this mean for the gas? Tell me, what this mean for the gas? It's the same. It's the same. So, any molecule randomly reaching this puncture or hole and chance to have access to this passage goes out. So some molecules may be very far, somehow accidentally can reach here. Some molecules even very closer to here may go the other way. Okay? Because of randomness. So, can you see some molecules very closely hitting? So, if it can find the way here out, that leaks. Okay? That leaks. This is very interesting. So, that's only leaks. So, there are parameters important for the gas leaks. Molecular size matter, because smaller size can easily. Then density of molecules, the denseness of molecules. More molecules means higher chances of okay, Buddha. More molecules means higher chances of reaching the hole. Okay, more molecules have higher chances when more molecules. Yeah. So that means more molecules means denseness of molecules. So this denseness, okay, this denseness of molecules. So when the denseness is there, okay, that's what we call pressure. Understand? High pressure, more leaks means there is no such thing, the denseness. That is important. Denseness, more molecules. Huh? So I take the word out, denseness. I leave the word denseness. And also the more violent, yeah, the violent, the kinetic nature. Okay? So higher movements of molecules, higher molecular motions. Movements or motions. Matter. Okay? Higher molecular motions. Denseness. So maybe it's energized. So you can see it as temperature or as pressure or combination. And of course, molecular size is matter. Okay? So why we are talking about this under this topic? Why are we talking about this under this topic? Yeah. Anyway, you can imagine even in a system, it is like this, molecules are there in a closed system. Molecules are there. That's how this behaves. Higher pressure, if you have a piston here, the piston moves. Okay, high molecular motions. What else? Yeah. So mainly these three. That's why you can see. So when it comes to refrigerants in cooling systems, let's see, working fluid in refrigeration systems. This is example. Example. Let's say example. R290 working fluid. Okay, has more higher risk of leaking compared to 600D. Example. Okay, that's why. So you can see that both have the higher pressures and so equal chance of getting leaks, no such thing. So everything matters. Okay. Yeah, so this is one example. So then how to check the leaks? Leak checking. Again, you have to look into the kinetics. Yeah. So if you can understand the gas leaks, you really know about the nature of gas. Only if you know the nature of gas, you can manage the systems very well. Yeah, you can manage the systems very well. If you have no understanding of gas leaks, even you cannot manage the leaks in your water tank. Even you cannot manage the leaks when a tire punctures. Yeah. So gas leaks means gas finding its own ways to escape. Okay. So at the same times, even external gas also can go in. Yeah. Low pressure, true, but sometimes some molecules, if smaller enough to go through, there may be a possibility. We cannot say no, but there may be a once in a million chance. External gas goes internal. Possible because all depends on the kinetics. Kinetics. If it can find the way, yeah, because same way, external gas also here. Okay. See, can go in. You cannot say no. Okay. Yeah, so these things are quite, how to say, quite nice to understand. Okay, Ritana? That's right. So even the regulators, how the regulators works and all. So you can think of this. Yeah. So pressure is not just a term for you. It's more than a measurement for you. Okay. And you know what makes the pressure. Yeah, what we call pressure. Yeah, that's right. So we talk about constant pressure. What constant pressure means for a molecule. What gas leak means for a molecule, not for us. Yeah. Thinking as a molecule, how molecule thinks about gas leak, you should understand that. Then you know gas leaks, you understand. What pressure means for molecules. Molecules understanding about pressure, if you have that understanding, you know about molecules, pressure and all. Okay with that? So this is little extra today. Quite interesting. So let me stop the class. Today we initiated this, let's say, summarizing, initiated this as a comparison. The reason is we have learned about the steady flow energy systems in previous session, and that is open systems. And then only we look into the closed systems. Yeah, it is quite okay, the practical approaches. Then we thought of comparing this. That's why we look into this too. Yeah. So you know that. Yeah. Closed system has no way mass in and out and has no way energy in and out with the mass flow. So you can have work in, work out, both net, let's say W, Q in out, everything, let's say Q. So towards the system from the surrounding is the standard convention or the standard of considering the direction of the work done and the heat transfer. Okay, because W goes to the system means energy level increase. Q goes to the system means internal energy level again increase. That's why, so whatever the energy level increasing results, that is the direction of W and Q. We consider that is the positive direction. So if W is positive, then of course work is done on the system. If W is negative, then so which means it is really performing work done out from the system. Okay, so the compressors have positive W and the turbines have negative W. Yeah. So it's the same thing. So delta T appears. You have Q for the closed system and the fixed volumes. Your W is denied, not allowed for a work done. And your boundary is fixed. Your energy balance comes. Q is delta U. You know that this kind of system, when you heat up, the temperature rise, that is the very basic. You feel the warmness. That's why, so any internal energy rise is proportional to the temperature rise. So here, for different substance to substance, this constant of proportionality can be different. So let's say that is CV. So that's about CV. Big CV is for the given mass M. CV by M is small CV, that is for kilojoule per kilogram per Kelvin. Oh, sorry, I made a miss. Yeah, okay, delta T. Yeah, okay, good. So this is after doing all, we came to this. So I believe you have some understanding of this, Putana. Then we go for this, how to say, constant pressure process. So I have to put this somewhere to make the note more clearer. Let me put it this way, because otherwise these words are hidden, that's why. So let me put it this way, nice. Okay, constant pressure systems. So there is a work done because when heats, molecules are more energized, their active movements are higher, momentums are more, change of momentums are higher again, and that exerts force on the boundaries, that turns into pressure. That's why you are here maintaining the constant pressure by allowing the system volume to change. So here your heat balance, energy balance, Q becomes delta H. But in the constant volume process, your Q becomes delta U. Constant volume process, your Q becomes delta U. Somewhere you see Q becomes delta U. So constant pressure process, Q becomes delta H. Quite interesting. So the same analysis here for constant pressure. So M delta H. So delta H is Cp delta T. So you recognize the C terms for constant pressure and C terms for constant volume. Okay. So That's it. Then again combining all big C's and small c's for V constant and for P constant. Yeah. So unchanged volumes and unchanged pressures. So that's it. And then you go for summary comparisons. All the terms are involved. So this is the master slide of today's discussion. See behind at a side delta T, top left corner. Don't forget. Yeah. So these are really time dependent. That's why you have delta for all because of this delta T. Yeah. This is the gas cylinder. The question, I think, answer is there. We consider this is only as a storage and no more process here. It's a storage, and when no liquid noise is there, when you shake, we consider empty because gas is 1,000 times lighter, let's say, at least 800, 900 times maybe lighter when you compare volume to the same volume of liquid. So this is just a storage only, and we recognize the pipe should go below the liquid levels. That is another important thing we recognize. The liquid pipe, it should be a liquid pipe, and of course we are charging liquid here. Empty bottle goes to the stations, they do charging in liquid form, charging in liquid form, not in gas form. It is not possible to fill gas cylinder in gas forms. It is very tough, and it's possible practically to fill gas cylinder in liquid form. Okay, that's a new knowledge for you. And understanding gas leaks, yeah, we have a little bit. Good. So you can feel that many things are not equations. Many things are not. Of course, you can write the equations, but when it comes to the reality, it's not about equations, but you can model it. So modeling is one thing. So this all are models. All are models. But we have to understand really how these molecules, gas all behaves, the thermodynamics of those. Yeah. Good, Putna. Let me stop the class now. Do you need this PowerPoint? Do you need this right now? Let me try to email. Kawgal Sadhane. File, CSV, PDF. If you need, I can send it to you. I can send it to you, Bhutana. But remember, you are given a very good note. You are given a very good note. So you can go through the notes as well. Corona है वो तो ताला बैठते. So we have here, we are from Kegol here. So we can see the situations here. It's not very good. I think all infections from the palliable cluster.
Excuse me, sir.
Yeah, puta.
Sir, මේ කලින් lecture වල presentation ටිකක් එවන්න පුළුවන්ද?
පුළුවන් පුතා. මම මේ දැන් එකේ වන්න බලන්නේ.
හරි sir. Thank you.
මේ දැන් එකේ වන්න බලන්නේ අනිත් ඒවාත් එවන්නන්නේ. අනිත් ඒවා ටිකක් තියෙන පුතා කැම්පස් එකේ. මට ඊමේල් ඇඩ්‍රස් එක කියන්න කොහොමද එන්නේ? කොහොමද එන්නේ ඊමේල් ඇඩ්‍රස් එක? මට මතක නෑනේ. UVT කියන්න පුතා ඊමේල් ඇඩ්‍රස් එක manufacturing and mechatronics කොහොමද එන්නේ? UVT 2K19 man එහෙමද? UVT Mech 19 okay හරිද? හරි වගේනේ. Yeah. Okay.
හරි සර් UOVT MEC 19 එන්නේ.
හරි පුතා.
Opposite.
Right. Okay. I got it. Today lecture slides. Face to face lecture එක කරනවා වගේ නැත්තා මේ කුමාරි තින් අපි ඉවසලා බලමු මේ වැඩි කරන්නේ මේ slides ටික මේ class lecture එකේදීම slides build up කරන එකේ තියෙන advantage එක. Because we are synchronizing our thoughts processes. Okay, we are synchronizing. So we all are thoughtful. Yeah, we are thinking of the same and try to understand. And whatever displayed on your screens are just an interface as a helping hand. But if I did the presentations in advance and just play the slides here, I don't think that is much useful. Anyway, try to understand the things beyond the textbooks. PDF drive කියලා කියවනේ පුතා වෙබ්සයිට් එක. ඒක තමයි එක්ස්පෝර්ට් තියෙන කියන්නේ අපිටත් එක්ක ඉගෙන ගන්නකෝ කට්ටිය කියවලා. සිරානේද? There are very good books on PDF drive. කීවද පුතාලාට ඒක නවම? කීවද? Did I mention to you about a website? Website එකක් ගැන කීවද? හොඳ free books download කරන්න පුළුවන්. කීවද පුතාලාට? කීවද පුතා නැද්ද? මේ කියපු එක ඇහුන්නේ නැහැ. කීවද?
No sir.
No. Oh my God. Without a key. Not taken a new one. Let me share with you that first. Actually, I should have done that. PDF drive. Let me share this. Yeah. This is PDF drive, and let's see if you need to look for thermodynamics books. Very good books, huh? Yeah. It's a thermodynamics and kinetics, all everything. So you can get see fluids and thermodynamics, guide to physics problems, fundamentals of thermodynamics, 8th edition. So this should be a very good book. Thermodynamics. Thermodynamics and statistical mechanics. So Senegal's book. This is a very good book. Thermodynamics. The Senegal. See, many downloads and small MBs. 40 MB means nothing for these grades books. Yeah, chemical engineering and thermodynamics, problems and solutions on thermodynamics. So you can see a lot of thermodynamics books. Let's say example. I'm going to download one. But anyway, my text is the text for you. Don't worry. See? So I click this 7th edition. Let's say I will look for download. See, checking for remote file health. මේක අනිකුත් nice sayings ටිකක් තියෙනවා. What is that chat? Okay, Buddha. So I can download. Let me download it. At the same time, make a chat වලක් තියෙනවා. හොඳ හරි ලස්සන දේවල් කියලා තියෙනවා. Some information from the books. No folly in folic acid. Now this is about the pregnant moms and people with the low immunity to disease. Folic acid prevents spine. It's found in green leafy vegetables. Information. Now we are downloading this book. Open when done. Let's see. Even your hobbies, there are books for the hobbies to improve your English, languages, Japanese, Korean, Chinese, whatever. You can see a lot of resources here. Modular subjects, you can pick up a lot of things, especially the languages, regional languages. Chinese, Koreans and Japanese is very good other than English. සමහර අය භාෂාවලට දක්ෂයි මම නම් දක්ෂ නෑ භාෂාවලට. But there are some, especially girls, they are very skillful in learning new language. You can see a lot of very good books, even exam focused ones. Language you can go overseas after your graduation. So you can plan for those. I mean, things are getting downloaded. It takes 7-8 minutes maybe. So bookmark this Buddha. Bookmark this PDF drive. Anyway, I will send you this in the chat. So that you can click it. So there are a lot of books, not only this. It's being downloaded. So at the same time, I will look for maybe music. If anyone loves music, it's a guitar. Let's say guitar. I'm searching. Music. See, music. Art. Because you should have some that kind of, because even skills, සංගීතය, කලාව, භාෂා, ඒවෙවිල්ල අර ඥාන කියලා කියන්නේ දුසා. How to say? See, arts, about arts. You can see a lot of books. Languages, let's see English. English. So if you type English, yeah, my signal is quite weak now. Yeah, so basic English grammar and all. Yeah, you can learn these things. You can download any book. Also C++, you have the programming. I mentioned you that programming is very important. Yeah, even C++ and that. There are other languages as well. I am using C sharp, but these days I didn't do any programs, but yeah, C++. You can see a lot of books here. So you can download, you can learn with the purpose. That is very important. Yeah. So not only for the exam, but this website is a very generous. Generous කියන්නේ බොහොම මේ හරි පරහිතකාමී විදිහට තමයි මේක වැඩ කරන්න පුතා මේක. It is quite good website. So we all are benefiting. Maybe the C sharp එකක් තියෙනවා. C sharp is a very good compiler. C sharp means C sharp කියන්නේ මෙහෙමයි. C sharp hash key එක වලින් නෝද C sharp I will show you. C sharp. C sharp. This is how C sharp. See? C sharp chords. You can pick up these things. It was a thermodynamics, some designs, technologies, refrigeration, heat exchangers, even how to design a rice cooker. Interesting, even how to use the ancient technologies with modern knowledge of thermodynamics or modern thermodynamics technologies. You can look for innovations even. So even innovations, there are maybe books. Innovations. How to innovate and all. You can see free books, but those are really valuable, really valuable. You don't undermine. Yeah, these are free but valuable books. Yeah. See the book already. Downloaded, start from here. Yeah. This looks somehow even. See, if you need to photocopy or scan, this takes time, but you can have a good book. Yeah. Still readable? Yeah. Somehow you can see the PDF. Yeah. There are very good PDFs. The original book, original print, PDFs there are. Yeah. So, very good. So, look for some books, very good ones. Nowadays, you can see a lot of practical oriented books are there. Oh, yeah. Good, Puta. Eh? Yeah. So, by this time, I hope you have received the notes. That's all for today. That's all for today. So let me stop the class now. Yeah. So any concerns these days about your concerns means if you have any issues in having access to internet or whatever, you all may have no computers. Some are using smartphones. Sometimes you may be borrowing the things. That is okay, Bhutan. If you can manage the thing, that is the greatest. And other difficulty tomorrow you will be stronger. ඉස්සර ගහලා තියෙන අර ලාම්පුකුත් පින්න අර ලාම්පුකුත් පින්න නෙවෙයි නිකම් මේ. පාරේ තියෙන ලයිට් කණුව ළඟට ගිහිල්ලා පාඩම් කරලා සක්සස්ෆුල් මිනිස්සු ඉන්නවා පුතා. කියවුවා රැට ලයිට් කණුව ළඟට ගිහිල්ලා. එන්නේ ගෙදරවත් ලයිට් එකක් නේ. ඒකට ඒ කාලේ මේ කාලේ ගත්තාම it's different. මේ කාලේ ගත්තාම similar situations can be there with internets or maybe modern electronics and all. So you have to look for somewhere else for the resources. That is okay, don't worry. Also having those things. Don't feel that good about having the gadgets also, because not everyone has the gadgets. Manage worry වෙන්න you will get better things in the future. So that is, we are pretty sure you will get much better facilities and all. So whatever hardships, that is okay. Whatever the hardships, that is okay. Don't worry. So that's the final message to you all. So be safe. Okay, be safe and help your families. And be active, be positive, and also be cautious and be safe. See you next Friday. If you have any concerns, you can email me. Don't worry. Okay, Bhutana. So let me stop the class. Bye then. Take care.
Bye, sir.
Right, done.